Hey guys, today we're going to look at rolling without slipping. Just want to take a look at a quick warm-up. A student playing on a merry-go-round. The merry-go-round is spinning clockwise, so that's this direction, with an increasing angular speed. Which blue arrow correctly shows the direction of the student's acceleration at the moment shown in the image? Okay, so you have these options, A, B, C, and D. Go ahead and pause the video and select an answer choice, and then we'll talk through it. All right, so hopefully you've made a selection. Let's think about what's happening for this student on the merry-go-round. It's traveling in a clockwise direction, so we definitely have a circular motion that's happening. In order to have a circular motion, you're going to need a centripetal acceleration for sure, right? So there has to be at least a centripetal component. So you might think that the answer is B, where the acceleration is pointing directly towards the center, but we also need to take into account that their angular speed is increasing. So again, they're traveling in a clockwise direction. So they have a clockwise angular acceleration alpha, which means their linear speed is also increasing. So not only do they have a centripetal acceleration, they also have a tangential acceleration in the direction that they're traveling. So that would be an AT that's making them speed up. So what I would say is this person needs both a centripetal component that is AC and also a tangential component that is helping them speed up. And together, that would make a hypotenuse equal to vector C. So the overall acceleration of this person is in the direction of C. It gives them both a turning component and a component that is speeding them up. Okay, so kind of think about what these other answer choices could be and why they're good distractors. D is technically the direction of tangent to the circle. So that could represent either the tangential velocity or the tangential acceleration. A, what would A represent? So A could actually be an acceleration if they were slowing down. So it would have a centripetal component that's helping them turn, and then also a component that's against their tangential velocity, and that would be slowing them down. So interesting distractors there, especially B, because it was directed towards the center, and you might be tempted to say, hey, it only needs a centripetal acceleration. But we need also a tangential acceleration to help us speed up. So just kind of revisiting circular motion, especially non-uniform circular motion where it can speed up or slow down, because the next thing we're going to get into is rolling. And the first thing I want you to do is just do a quick lab. If you have a meter stick or a roller, just take something like a quarter, something that's circular, and determine the relationship between the number of rotations and the linear distance that's traveled if you just roll that quarter on next to or on top of a meter stick or a ruler so that you can measure the distance. So I would ask that you kind of take a pause on the video, go complete that lab, and then come back to this video and we'll go ahead and talk through the results. Okay. All right, guys, welcome back. Hopefully you were able to do that lab and you got a nice relationship. And basically what you should have found in the lab is that for each rotation of the wheel or the circle, then you should travel one circumference. So one rotation should lead to one circumference traveled by your wheel. Okay, so now I want you to try this little activity. If you were to take two circles of the same radius and put them next to each other and just kind of pin one of them down. And I'd like to see, if I have these two quarters here, how many rotations will this quarter go through in returning to its original position? So one revolution around the bottom circle, how many rotations is it going to make? So go ahead and take a guess, and then put two quarters together or two circles of the same radius and go ahead and revolve one around the other, rolling it around and see how many you get. Okay. All right, so let's see. Maybe you were surprised by that result when you did that, and that leads us to this 1982 SAT question. Always like to bring this one up when we do rolling. Circle A has 1/3 the radius of circle B. Circle A rolls around circle B, so very similar to the activity you just did. except that these two circles have different radii. And the 5 answer choices that were given in 1982 are 3 halves, 3, 6, 9 halves, and 9s. That's the number of revolutions of circle A in returning to its original position. So if you want to pause the video and try this one, see if you get one of these answer choices. Okay, so the reason why this 1982 SAT question is so famous is that after the SAT was over, there was a handful of students who wrote letters to the College Board and said there were some issues, I think, with this question, and they actually put together a really nice proof, and they were able to show that the correct answer was not actually one of the answer choices. So it's in 1982, not one single person got this one correct because the correct answer choice was not given. So I'd like to go through this one with you. If circle A is 1/3 the radius of circle B, what I'd like to write is the radius of B is 3 times that of radius A. Okay. And when we think about rolling, and when you did the quarters back here, you may have thought, well, because it travels one circumference in one rotation, you may have thought that it's only going to rotate one time. But what's interesting is it's the center of mass that is actually traveling that distance of one circumference for one rotation. Okay, so where you may have said, well, this circle needs to just travel this distance, which would be one circle or one circumference, it's the center of mass that's traveling that linear distance, right? So when I think about this problem right here, circle A is traveling around this circle right here. So the distance that it needs to travel is actually a circumference of radius of B plus the radius of A. And if we track the linear motion of the center of mass, we would say that the distance traveled for one full revolution is going to be 2 pi times RA plus RB. And remember that we said that RB is 3 times RA. So that means the total distance traveled by the center of mass is 2 pi times 3 RA plus RA. So that's, again, just the radius of B plus the radius of A. And that would be 3 plus 1 is 4 times 2 is 8. That's 8 pi RA. So the total distance traveled is 8 pi RA. And to get the number of rotations, we would take the total distance traveled by the circumference of circle A, right? Because every time it rotates, it will have gone one circumference. The center of mass will have traveled one circumference. So I'm going to take that 8 pi RA, and I'm going to divide it by the circumference of circle A, which would just be 2 pi RA. And it turns out here the RAs are going to cancel, the pi's are going to cancel, and it would rotate 4 times. So if you would like to try that, just to make yourself feel more comfortable with this SAT question, you could cut 2 circles. One circle needs to have 3 times the radius of the smaller one. And as circle A rotates around circle B, you're going to see that it would actually go 4 full revolutions as it goes around circle B. So when we do rolling, just remember, keep in mind that it is the center of mass that's traveling, that's covering that distance. So when we look at one rotation is equal to one circumference traveled, it's the center of mass that is traveling that distance. Okay, and that sets us up for what we call rolling without slipping. Rolling without slipping means if you are accelerating, it is due to a static friction and not a kinetic friction. So again, our definition of static and kinetic is not moving and not moving. Static can be moving, as we've seen, like if you're standing on a skateboard that's moving. Static just means that the materials are not moving relative to each other. So for an object that's rolling without slipping, as the wheel rotates, the center of mass continues translating forward. And for one revolution of the tire, the center of mass should move one circumference. That's what we mean by rolling without slipping. The center of mass moves one circumference for each rotation. And when that is true, when those conditions are held, then we know that the translational velocity of the center of mass is going to be equal to omega r. It's going to be related to the angular speed of the rotation of the wheel. And we also know that the translational acceleration is going to equal alpha times r. So those relationships between the linear terms and the angular terms are going to hold true if we're rolling without slipping. So what can happen, like, if you were in a car and you press the gas pedal too hard, you might feel like a burnout where your wheels spin too fast and your car doesn't move forward one circumference for every rotation of the wheel, right? That's rolling with slipping. And that would be kinetic friction. And you see all this smoke come up because there's this thermal energy that's, stealing from your mechanical energy when you have kinetic friction. But as long as you are accelerating at reasonable rates, then we can continue having static friction, and our translational and velocity and acceleration are going to be related to the angular velocity and acceleration of the wheel. So what we'll look at next are conditions where this is broken, where, at what point does the object start to slip? And it will just be the moment when these conditions no longer hold. It would turn into rolling with slipping, and it would be kinetic friction instead of static. Okay, so that is it for defining rolling without slipping. Thanks for watching.